Oh, you're right. I should write this in terms of x and y. My bad. Let me put x's and y's here. It looks like you're actually doing something when you change a and b to x and y. Let's do that. So x, y. All right. Then if we look at eta at the point xy prime of 0, we should be able to calculate that. Man, fine. Cos tx, good grief, x cos t minus y sine t, x sine t plus y cos t. All right, so when I differentiate that curve with respect to time, and then I plug in time 0, I get a minus y for the first one, which gives me minus y partial x, and this one gives me plus x partial y. So that, of course, is w, right? W is the infinitesimal generator of that flow. That flow is nothing more than rotate the plane by an angle theta. The other flow, for example 1, is translate the plane by t, right? So far, so good? All right, let's go on. Now, I need to erase something. I think we can erase all this, it's fine. So I do owe you that example. So here's my example 5, I guess. So this is a not a complete vector field. Let's see how that could happen. This gives us another illustration of the calculational method. So suppose you got w is equal to x squared partial x. All right? So if we're trying to find the integral curves of this, how does that go? We need to solve dx dt equals to x squared and dy dt equals to 0. All right? Going back to, is that okay? Do you guys see what I did? Do I need to write it out again? So like if this is equal to d gamma dt, which is dx dt partial x plus dy dt partial y, then I equate the coefficients of partial x and partial y, and that gives me the differential equations I have to solve to find the integral vector field, the integral curves to said vector field. So this is easy. Y equals y naught. Okay, done. Right? This, on the other hand, we know how to solve. See, because we've got dx over x squared is equal to dt. Integrate from x naught to xf. Integrate from, say, times 0 to times tf. So that gives me minus 1 over xf plus 1 over x naught is equal to tf, which then gives me that 1 over x is equal to 1 over x naught minus t. I've taken the liberty of setting tf equals to t and xf equals to x. Flip it. We get x is equal to 1 over x naught minus t, which will give us x naught over 1 minus tx naught. So altogether, we've got gamma of t is equal to x naught over 1 minus tx naught, comma y naught. So there you go. That's the integral curve that we find for this vector field at the point x naught, y naught. What's its domain? Let's, suppose x naught is positive for the sake of, discussion. If that's the case, what's the domain? I mean, like, we can't have 1 minus tx naught equal to 0, right? That would be trouble. Which means we can't have t can't be equal to what? 1, I think t can't be equal to 1 over x naught, right? So looks like the domain of gamma would naturally be 1 over x naught not included. Excuse me, well, I guess we could do minus infinity to 1 over x naught maybe? That might be okay. I'm not sure. I haven't investigated it too deeply. In the book, he just looks at this example for a specific, he just looks at the point 1, 0. So like like the text looks at x naught, y naught equals to 1, 0. So his integral curve just has, it looks a little nicer. It's just like 1 over 1 minus t comma 0. And he argues that that's the integral curve for this vector field. And it has a domain which can't be extended past 1. What makes this example so very interesting is like the fact that you can't extend the domain past that, right? But you don't see that, at least I don't see it, manifestly in the original vector field. So it's not altogether obvious which vector fields are complete and which ones are not, just from just a surface level glance. Like, this is a relatively simple vector field, but it's not complete. However, good news, the left invariant vector fields on a Lie group are complete. So that's one thing. So if you're looking at left invariant vector fields on a Lie group, they're complete. And I'm just skipping over like a bunch of, there's like really neat theorems about how if you have a global flow on a manifold, right? If you have a global flow on a manifold, I think I may have forgot to move the camera. Oops. Sorry, people at home. My bad. If you have a global flow on a manifold and you have a diffeomorphism to another manifold, guess what? If you just take the flow and just map it over to the other diffeomorphic manifold, you get a global flow on the other manifold. So there's nice like transport of flow theorems, and yeah. All right, and like I said, every left invariant vector field on a Lie group is complete. So this thing doesn't happen for the left invariant vector fields on a Lie group, which is super nice. Next thing he talks about are called flowouts. So flowouts. Flowouts. And let me just write a sentence on that. So for M smooth manifold with S a submanifold and embedded k-dimensional submanifold. And if we also have V, a smooth vector field on M, which is nowhere tangent to S, we may construct. And I'm not going to get into the details because the details involve homotopy. which is something that's a little bit beyond this course, right? Unless we stop and do homotopy here later, but I don't know. You guys could probably talk me into it if you wanted to, but short of being talked into it, I'm not going to do it. What's homotopy? Homotopy is actually the part of topology that's about smoothly deforming one thing into another. Like those pictures you've seen about coffee cups becoming donuts. That's there you go. That's homotopy. It's a continuous family of deformations that takes you from point A to point B in your topological storytelling. So then we may construct, and I'll use Lee's notation. Wait, I'm not going to explain this notation. I'm just telling you what he calls it, okay? Phi, funny looking O, sub delta. And I'm going to call that, for the sake of discussion, flow along the vector field V of S, because that's what's going on. That is itself a submanifold of M. So, and this is called the flow out from S along V. Flow out from S along V. Now, so like a picture of what that is something like this, guys. So if your manifold maybe is like something like this, and maybe this, so the picture he has is something like this. This is S, the submanifold, all right? Okay? And then if we draw the integral curves for the flow, something like this, then the flow out is literally something like this. Let's see if I could think of another example. Let me here's some example, 3 dimensions. If our submanifold was perhaps this line, right? And I was to look at the flow out of, say I look at the flow that's integral to the vector field partial z, right? Suppose partial z is the infinitesimal generator of a flow, right? Well, anyway, suppose I look at the vector field partial z. The flow out of this submanifold, which is just a curve, would be like this. It would be a vertical plane. That's the flow out. Basically, you're just taking the submanifold you start with and extending it by flowing along the vector field. This is something you can do. And in so doing, create a submanifold of 1 dimension larger. Part D of his theorem, he says that if you have a hypersurface, if you've got a submanifold of codimension 1, and you look at the flow out of that, you'll get an open submanifold of the manifold. In other words, you get a manifold of the same dimension as M. And the reason you don't get the whole thing is like the flow outs that are talked about, the flows which are talked about, they're not for a complete vector field. This is for a vector field which it might only flow so far, like the one I just erased. Well, this would be a diagonal. I'm foolishly attempting to picture the diagonal plane.
But I mean like tilted.
Well, sure, yeah. I mean, if instead I had like partial z plus partial y, then that would give me a different flow out. If I had partial x, it would just like, I don't know, as much as you can read this, but he also defines a singular point. What's a singular point to a vector field? singular point to V is V in the smooth, so V is a smooth vector field, okay? Is P in M such that V sub P equals to 0. Else P is regular point. All right. And then proposition 9.21 says that if you have a singular point and you look at the flow of a singular point along, like the orbit of the singular point along the flow of the vector field, you just get the constant curve. It like just sits put. It doesn't go anywhere. On the other hand, if you look at the flow of a regular point along the flow generated by the vector field, then you get a smooth immersion, is what he says in proposition 9.1. Then theorem 9.22, the only other thing I wanted to tell you guys here is this is an interesting result. Theorem 9.22 says that V is equal to the coordinate derivation for the first coordinate near regular point. So let me put that into more sort of easy to understand words. If you have a vector field, all right, and it's not 0, smooth vector field not 0, then there exists a coordinate system at that point for which the vector field just becomes the derivation with respect to the first coordinate. And actually theorem 9.22 tells you more. It tells you can set up like this system of slice coordinates that blah, blah, blah. There's like more bells and whistles to it, but that's the big idea. All right, so that's what I would say about that. Now, the really interesting part comes with theorem 9.29. Theorem 9.29, which I'm going to erase this business here. It gives you the rudiments of what's called surgery on manifolds. Can you guys tell me how to spell surgery? I've forgotten. All right, it's on you guys now. Surgery. Is there two U's in surgery?
No.
Okay, good.
That's it.
That's it? All right, cool. Surgery on manifolds. And like, so here's the deal. You've got M and N smooth N manifolds. All right. You've got H diffeomorphism, which maps the boundary of M to the boundary of N. All right. Then you can define this thing, M glued together using H to N, is a smooth manifold, which is equal to M prime union N prime, where M prime is diffeomorphic to M, and N prime diffeomorphic to N. All right. And furthermore, well, like I said, it's the union. But if you look at the intersection of M prime and N prime, you get the boundary of M prime, which is equal to the boundary of N prime. So, excuse me, this is, and the way this is done is using the flow stuff. He explains how you can build these colored neighborhoods of the manifold using the flow concept. It's built. These things are built using the technology of this chapter. And if you were to take a course on differential topology in graduate school, you'd probably get into this much more deeply, because these are some of the tools which are used to construct interesting manifolds. We can actually do that, though. Let's actually look at how that goes, like a little bit more. You guys will understand this. It's not bad. So if I had two, let's say I had two connected manifolds, or just two manifolds. So like example, what are we on, example 6? So if you have like M1 and M2, two n manifolds, all right? And you have U1, a subset of M1, and U2, a subset of M2, and these are coordinate ball. Remember he defined coordinate balls earlier in the book? So a coordinate ball is something that's diffeomorphic to the unit sphere in N and Rn, right? So what he does then, he's like, oh, okay, so if we take M prime equals to like, well, M1 prime equal to M1 with U1 deleted, and if you take M2 prime equal to M2 with U2 deleted, then the boundary of M1 prime is Sn minus 1. And the boundary of M2 prime is Sn minus 1 up to diffeomorphism. Yeah. So they have the same boundary. So obviously they're diffeomorphic, which means then you can use this theorem to attach them. So the idea is you start with M1. Let me make it more exciting. You start with M1. I'll put a hole in it over here. There, now you know it's real. And over here is M2. And I'll put a hole in it here. There you go. And then you cut a ball out of it, right? And you cut a ball out of this one, right? You delete those. Now they've got a boundary. Both of these manifolds have boundaries, right? And I think that if I remember, they might have been smooth manifolds without boundary to start with. Because I think, yeah, I think these are, let's let them be manifolds without boundary. That just to be sure. Okay, so, and then what's done is you just connect. You know, you just identify these points, glue those together along where they've been cut. Now you've got a bigger manifold, which is formed by the so-called connected sum of the two.
And you just get rid of the area that you cut out?
Well, technically speaking, the new manifold's formed by an equivalence class of things. And the equivalence class is just stupid. It identifies points with itself, except for the points that are here and here, which are identified with each other. And then you have to, you know, suitably extend things past that. But so anyway, this is the connected sum of two manifolds. You just cut a piece out of one, cut a piece out of the other, and glue them on the matching cuts. Surgery. And then the other thing that's really cool is you can talk about the double of any manifold. If you've got a manifold with boundary, right? What you do is just take another copy of the same manifold with boundary. If it's got the same boundary, the boundary's diffeomorphic to the same thing, you just glue it to the boundary. So like, if your manifold was like this, right? And you had a boundary like that, you know, that was your boundary, then you just take another copy of it, you know, and take that same boundary and just connect them just like that. Through this apparatus, you get a new manifold called the double. What's the boundary of the double of a manifold? See, that's the interesting thing, is in this process, what was previously a boundary of M, so this is technically like the disjoint union of M with M, like that. He calls it M union with identity on M. Here the identity is the mapping from the boundary of M to the boundary of M to define the double of M. This is the double of M according to the book. But in the double of M, there's no boundary. That's right. So if you want to, oh come on, I was robbed. I was robbed. If you want a manifold that has the same interior of a given manifold with boundary, but no boundary. We'll just look at the double. Anyway, this stuff is, so I asked my student who went to grad school for various kinds of, I was asking him about, Audric, about, how to find manifolds with particular, fundamental groups. This is the stuff he was using to build examples, in part. So that brings us to Lie derivatives.
What happened to the boundary?
What's that?
What happened to the boundary? I
I
eated it.
eated it, yeah. All right, so you got to go. Let's see here.
I can watch.
You can watch? Okay. Because I probably about like 10 more minutes. Then we'll be done. I don't have too much to say about Lie derivatives at the moment. I just want to introduce the concept. So he has a really nice lead up into it on page 227. But essentially, the purpose of the Lie derivative is to compare two vector fields. To compare two vector fields. And so, man, this board is just a mess, isn't it?
I wonder if somebody like eraser again.
Is that what it is? You think it's years of the board being spranoed? Let's see here. It's a verb. It works. Let's see here. I love Dr. Sprano. Let's see here. So, yeah. I'm sure Dr. Sprano has better things to do in his life than ever watch my videos. But I only watch them when I forget, which is often. What did I do in this course? Oh, that's what I did. So anyway, all right, so if you have two vector fields and you want to compare them. You want to see how one vector field changes in the direction of another. That's the question that the Lie derivative answers. So there's a way of calculating that straight away in like Rn that doesn't make sense in a manifold because you just can't move vectors around in a manifold. But the definition, which is given, which I'm just going to write down and then we'll never use it probably, except conceptually, is this. The Lie derivative in the v direction of w, all right, at the point P is equal to d dt at time 0 of the differential of the flow at minus t of, and this is a mess, theta sub t of p. I remember doing homework on this stuff in grad school. It did not give me joy. W theta sub t of p, what a mess, like that. So essentially what's going on is that you're using the flow. Here theta is the flow along v, I believe. Yeah, theta is the flow of v. So you're using the flow of v to compare. You're comparing values of the vector field w at one point and another, and then basically calculating the usual difference quotient kind of thing. That's what this is. And there's about a half a page in John Lee that motivates it. But he's got a lemma. 9.36, if you have M, a smooth manifold with or without boundary, and V and W are vector, smooth vector fields on M, and if the boundary of the manifold is non-empty, if you assume in addition that V is tangent to the boundary of M, then the Lie derivative exists. Okay, so lemma 9.36 in a nutshell says, hey, this still makes sense for manifolds with boundary, appropriately so. Great. What I was getting to, this is what makes this. Like if this was all we could say about the Lie derivative, I wouldn't bother. I just don't have enough patience to do too much with that. But here's it. If M if you've got V and W smooth vector fields on a manifold, then the Lie derivative of V with respect to W, of W with respect to V is, get this, the commutator of V and W. So it's literally, the Lie derivative is the Lie bracket. So that's not bad. Not bad at all. And it has wonderful properties. So corollary. So the property, the properties is just a corollary because basically all these properties are just straight away lifted, completely just stolen from what we already did with the Lie bracket. So, but this kind of makes sense intuitively speaking if you think about it. How should the change in V with respect to W be related to the change in W with respect to V? Mm-hmm. Exactly. So there's the proof right here. Check it out, yo. It's not bad. So there you go. There's that one. B, the Lie derivative in the V direction of the commutator of W and X is the commutator of the Lie derivative in the V direction of W with X. And I say commutator, but I should really be saying Lie bracket, as per my previous admonishments of myself. Oh, look at this one. These all look like fun exercises. See, these I think would be fun homework problems. So this is, so the Lie derivative in the commutator direction of X turns out to be equal to, check this out, LV of LW. Oh, you know what this is? This is the Jacobi identity. That's what this is. And then D, for G, a smooth function, the Lie derivative in the V direction of GW is equal to V acting on GW plus G acting, well, G times the Lie derivative of V of X. All right. Wait, where's the X coming from? My bad, W. Just a second. Let me make sure I'm not inadvertently combining them. Oh, and then finally E, last but not least, if you've got a diffeomorphism, the push forward, oh, check this out. The push forward of the Lie derivative of V in the X direction is, guess what? It is the Lie derivative in the push forward direction of V of the push forward of X. So you got your choice. You can either calculate the change of X in the V direction in the original manifold, or you can calculate the change of the push forward of X in the push forward direction over there. But they're the same. This is for f of diffeomorphism. So there's that. And then we're getting back to one of the questions I posed like in a previous lecture about given a couple of vector fields, is it possible that they're coordinate vector fields, right? So we've partially answered that question with the theorem that I think I erased over there, the theorem 9.21, which said that if you have a non-zero vector field, there exists a coordinate system such that it is the partial derivative with respect to S1, right? So that's like part of what we need. But the question was, if you have vector field V and a vector field W, is it the case that you can find a coordinate system where v is partial partial s1 and v is partial partial s2? Like, is that possible? So we're about to find an answer to that question here. This is the section on commuting vector fields. And I'll get straight to the point here, which is that this is the theorem 9.42, which says the following. For V and W smooth vector fields on the manifold, the following are equivalent. I did that the other day in physics. They were like, what's that? It's like, the following are equivalent. V and W commute. Oh, but I like to. So W is invariant under flow of V. V is invariant under flow of W. That seems kind of redundant. I guess I missed a definition though. What does it mean for a vector? What does it mean for it to be invariant? So the definition of that was right in the paragraph before that, which is this. W is invariant under the flow theta if W is theta sub t related to itself for all t. Okay. So remember, the flow gives you a diffeomorphism of the manifold to itself. So then it makes sense to, it gives you a smooth, not a diffeomorphism, well yeah, I think it was diffeomorphism. It gives you a diffeomorphism from the manifold to itself. So it makes sense to ask the question, is W theta t related to itself? Because theta t is a diffeomorphism from M to M. So we can ask that question. And so that's what's meant by these two things up here. Anyway, I do actually want to finish, sorry. Getting to the point eventually. Corollary 9.43, every smooth vector field is invariant under its own flow. Okay, great. And here's the theorem 9.44. Smooth vector fields commute if and only if their flows commute. All right. So you might wonder, what does it mean for flows to commute? The flows commuting means this. Theta t composed with psi s is equal to psi s composed with theta t. And so you can make a kind of like what's called a flow box. You can walk a little bit along the theta direction and a little bit along the psi direction and compare, you know. So this is saying that if you went, maybe this is the theta one, and then like this would be psi s. What would be this? So that would be maybe like this, then that. If I start with a point P, right? Or on the other hand, you could do start with P, do the psi s first, and then do the theta t second, right? But if they're equal, then the flows commute. If they're not, they don't have to be equal, you see. For two vector fields, it could be that when you do the flow this way and then that way versus the other way, that you don't end up back at the same point. They don't have to be the same. But they do have to be the same if the smooth vector fields for which the flows commute. It turns out that that is what you need in order to set up a coordinate system where the S1 and the S2 like the S1 and S2 coordinates are the derivations that match the given vector fields, which give you these commuting. If you have the commuting flows, you can set up the coordinate system, which makes the two first coordinates in the coordinate system like partial S1, partial S2, because of basically this. And that what brings him to the next section, which is commuting frames. What's a commuting frame? A commuting frame is a frame of vector fields whose Lie bracket is 0, pairwise 0 between any pair of the brackets. And the big theorem here is theorem 9.46, which says if you have a smooth manifold and you have linearly independent k-tuple of smooth commuting vector fields on an open subset, then there exists a smooth coordinate chart which will give you v1 is partial S1, v2 is partial S2, vk is partial sk. So the answer to my question that I asked the other day, whether or not it's possible to make a given set of vector fields, coordinate vector fields, that is answered by calculating the Lie bracket, the pairwise Lie bracket of all the, if the pairwise Lie bracket of all the vector fields is 0, that's enough. It turns out that there is a more subtle condition that they can satisfy and you can still get this condition. But certainly the vanishing of all the Lie brackets is a sufficient condition. This later leads us to the discussion of what's called the Frobenius theorem later in the course. There we'll talk about what's called the involutive condition. And there's more to say, but this is the first and easiest version of that theorem. So it's a nice result. And then what remains in this chapter, and he actually does have examples of, one of the things weirding me out is he said that anyway, I should look at those examples again, but there's a couple examples. If I had more time, I'd do, but I think we're out of time. So the remainder of the chapter, he's got a section on time-dependent vector fields, which is fascinating. And the very end of the chapter, he describes some ways we can use flows to solve partial differential equations, and the so-called method of characteristics. That's very interesting, but I don't think it belongs in our course. So next time, I will hopefully go on to, oops, my bad. I was zoomed in too much. Oh, I said I'd also cover chapter 10, so I guess I should do that. Chapter 10 is on vector bundles. What's a vector bundle? Manifold, you have a vector space over each point, and they're connected together in a natural fashion. That's pretty much it. That's what chapter 10 is. I would have talked more about it, but as I look through his list of homework problems, I can't find any that are course appropriate, so that's like why I'm kind of skipping chapter 10. We'll introduce the language from chapter 10 as we need it going forward, okay? That's pretty much maybe like the first 3 pages in chapter 10 you need to read. I don't even that. We'll get back to it when we get to it. That's enough for one day. So sorry guys, I'll stop.